Yes, hello friends. See the continuation. I'm discussing AC bridges. Now we'll see the next concept with respect to AC bridges. Concentrate on types of AC bridges. Yes, types of AC bridges. Okay, one is inductance bridges. Inductance bridges. Okay, the inductance bridges. One is Maxwell's inductance bridge. Maxwell's inductance bridge. Another one is Maxwell's LC bridge. Maxwell's LC bridge. Another one is Maxwell's inductance bridge, Maxwell's LC bridge, Hayes bridge, Hayes bridge, S. Anderson's bridge, Anderson's bridge. Another one is Owen's bridge, Owen's bridge. All these are the inductance bridges. The next one is capacitance bridges. Capacitance bridges. Okay, what are the different types of capacitance bridges we are using? One is de Sauty's bridge, de Sauty's bridge, sharing bridge, sharing bridge. The third one is frequency bridge, frequency bridge. That is Wien's bridge. Wien's bridge is the frequency bridge. The fourth one is mutual inductance bridges. Mutual inductance bridges. Okay, in mutual inductance bridges, one is Campbell's and Heaviside bridge, Heaviside bridge. Another one is Carey-Foster and Hidwiller bridge, Carey-Foster and Hidwiller bridge. Campbell's and Heaviside bridge, Carey-Foster and Hidwiller bridge. Okay, these are the different types of AC bridges we are using. One model of questions asking in competitive exam based on this concept is, which of the following bridge is used for measurement of inductance? Which of the following bridge is used for measurement of capacitance? A Wien's bridge is used for measurement of dash. Owen's bridge is used for measurement of dash. That type of questions are asking in competitive exam. To solve those questions, one method is you can by heart all these bridges, then you can answer. That is one way to answer. But you go for elimination method also. If you forget that, then how to answer in elimination method, that I want to explain. But it is not a concept. For remembering purpose, I am giving this. Okay. Don't think as it is a measurement concept. For remembering purpose, I am giving how to answer in elimination method. See, you remember only these two bridges. Mutual inductance bridges you remember. Campbell's and Heaviside bridge, Carey-Foster and Hidwiller bridges, mutual inductance bridges, that you know. That means by seeing these bridges you easily identify. But sometimes, still now, if you see the previous competitive exam questions, wherever the question is asked based on the mutual inductance bridge, which of the following is a mutual inductance bridge, like that it is asked. They given combination of names only. In the options they given combination of names. Yes. If every time if they give like this, no need to remember even mutual inductance bridge also. The bridge which given in combination of names, then it is a mutual inductance bridge. But sometimes you don't expect, always you don't expect like that only, because in developing of mutual inductance bridge, Campbell's and Heaviside combination one bridge is developed. Campbell's and Heaviside separately they developed the one mutual inductance bridge. Sometimes we may expect single name also. That's the reason why, to eliminate that confusion, I am telling that you remember only mutual inductance bridges. You remember only. That means you know we can easily identify the mutual inductance bridges because you know that bridges. But remaining bridges, without remembering also, just by seeing the bridge we can easily identify. By given name you can easily identify. Then how to identify frequency bridge means, in frequency bridges, which is the frequency bridge? Wien's bridge. In Wien's bridge, which is the starting letter? W. W is nothing but a, let assume that omega. Omega is nothing but a frequency. Okay, no need to remember this bridge. This over. Next, how to remember capacitance bridges? In capacitance, you know the property of capacitor is capacitor charging and discharging. Remember as the term discharging. Discharging. Okay, this is not concept. For remembering purpose in a competitive point of view, that objective point of view, I am telling that. Capacitance, there is a concept of charging and discharging. Discharging. DS bridges are capacitance bridges. DS bridges are capacitance bridges. That's why D sort is bridge and sharing bridge. That's why no need to remember capacitance bridge also, we can easily identify just by remembering the discharging term. Then remaining all the bridges are inductance bridges. Whatever the remaining bridges are there, remaining all the bridges are inductance. Like that we can remember. Okay. Then you already know the mutual inductance bridges. How to remember frequency bridge you know. How to remember capacitance bridges you know. Remaining all the bridges are the inductance bridges. Clear? Sir, in Wheatstone bridge also W is there. Then is it a frequency? See, Wheatstone bridge, resistance bridge, all are familiar that one. Wheatstone bridge, frequency bridge means that is meaningless. All are familiar. We are studying from 10 plus 2. Okay, that Wheatstone bridge. Okay, that's why even who are taking the from 6th class or 7th class onwards, who are taking the IIT coaching, that students are studying even 6th class also they are studying a Wheatstone bridge. Okay, that is meaningless. Okay, but Wien's bridge is the frequency bridge that you know. See, with this knowledge, I will give one or two questions, then you get idea how to approach in elimination method. Okay, for example, if the question asks like this, this is the second model of questions. In all the competitive exams, this model is already framed, important model. Okay, which of the following bridge? Which of the following bridge is used to measure inductance? In general, inductance means you take self-inductance only. If it is mentioned that mutual inductance, then only you take mutual. To measure inductance. Which of the following bridge is used to measure the inductance? Option A. Hayes bridge. Option B, sharing bridge. Sharing bridge. Option C, okay, Wien's bridge. Wien's bridge. Option D, Hidwiller bridge. Hidwiller bridge. The options are given like this. Then what is your answer? Go for elimination method. Yes, Hidwiller bridge is your remembering bridge. You already remember this bridge. This bridge is a mutual inductance bridge that you know already. That's why it is not the answer. Wien's bridge, W omega frequency. That's why it is not a inductance bridge. Sharing bridge, capacitor discharging, DS, S starting letter is there. That's why it is not a. Then your answer is Hayes bridge. Like that you answer. Clear? For example, example 2. Okay, Owen's bridge is used for measurement of dash. Owen's bridge is used for measurement of dash. Measurement of dash. Option A, L. Option B, M. Option C, F. Option D, C. Owen's bridge is not your remembering bridge, and it is not a combination of names. That's why it is not a mutual inductance. Owen's bridge starting letter is not a W. That's why it is not a frequency bridge. Okay, Owen's bridge is not a DS bridge. That's why it is not a capacitance. That's your answer is inductance. Like this you can answer. One more example. Which of the following bridge? Which of the following bridge? Following bridge is used to measure mutual inductance. To measure mutual inductance. Which of the following bridge is used to measure mutual inductance? The options are given like this. Option A, Wien's bridge. Option B, Campbell's and Heaviside bridge. Campbell's and Heaviside bridge. Head bridge. Option C, Anderson's bridge. Anderson's bridge. Option D, Maxwell's bridge. Maxwell's bridge. Then what is the option, you tell me? This is already your remembering bridge, that's why you can easily answer. And if the options are given like this, again very easy to identify, because these are combination of names is given, that your answer is Campbell's and Heaviside bridge is the mutual inductance bridge. Like this we can answer any question. Okay, this is one model of questions asking in competitive exam. In all the competitive exam, these models are repeated. This is very important. This 1 mark questions very important for any competitive point of view. In engineering service exam, every year compulsory 1 or 2 questions based on this one. Even in GATE exams also already asked based on this one. In other competitive exams also it is very important. This model is important. Okay, this about what exactly different types of AC bridge. Now I want to discuss in detail about each bridge. Before starting in detail about each bridge, mainly here I want to discuss 2 important factors here. What is quality factor, what is the significance of quality factor, and what is the dissipation factor, and what is the significance of dissipation factor. After discussing that in detail about each bridge, we will start. First we will start the inductance bridges, then remaining bridges we will see. Okay, first we will see I want to discuss some significance of quality factor and dissipation factor. Yes. First you concentrate what is the quality factor. Quality factor Q. Yes. It indicates the quality of a inductor. You know this one? It indicates or it measures the quality of a inductor. Given inductive coil, how much quality? It measures the quality of inductor. Okay. Yes. The point to remember, the quality factor measures the quality of inductor. Quality factor is measured at resonance condition. Q is measured at resonance condition. Yes, measured at resonance condition. This you know. Resonance condition. Yes, tell me. Then the fundamental formula for quality factor equal to 2 pi into energy stored by inductor by energy dissipated by resistance of inductor. Q equal 2 pi into energy stored by inductor by energy dissipated by resistance of inductor. This is the fundamental formula for quality factor. Okay. We know that quality factor is more accurately measured by inductance bridges. If you want to measure the quality factor more accurately, then we can use some inductance bridges, but it is a less time consuming. And quality factor is directly measured by Q meter, that I already discussed. Quality factor is directly measured by Q factor. That means quality factor is more accurately measured by inductance bridges, but it is time consuming. That is the drawback of using bridges to measure the quality factor. Quality factor is directly measured by which one? Q meter. That means the deflection of a pointer directly indicates. But here if you want to measure the quality factor using bridges, means you can bring that coil, connect in any one arm, then bring the bridges balance condition, then apply the formula, then you can. That is a time consuming process. That's why quality factor is directly measured by Q meter. The deflection of a pointer directly shows the reading. But the problem is less accurate. Okay, this is the selection in order to measure the quality factor using bridges and Q meter. Okay. Then if it is a series RL coil, how to write the quality factor? Q equal to XL by R, or Q equal to generalized formula that you know according to resonance condition, omega L by R. This is XL by R. You also write G by BL. If it is a parallel RL coil representation, this is series RL, and if it is a parallel RL, then you write quality factor equal to R by omega L. This is R by XL, that equal to BL by G. This you write. or in term, this quality factor is measured at resonance condition. For resonance of any circuit, there must be one inductor and capacitor. This formula can also be written using capacitance. Q equal to 1 by omega CR. Okay, this equal to XC by R. That equal to G by BC. This also you write in terms of capacitance. Quality factor equal to omega CR. That is R by XC. That is BC by G. Susceptance of capacitance by conductance. Okay, like this you can write. But point to remember, based on quality factor, the inductive coils are classified into three types. This is important with respect to measurement point of view. That is, based on quality factor. Yes, based on quality factor, the inductive coils are classified into one is low Q coils, that is low quality factor coils. Low quality factor coils. The range of quality factor coils is, low Q coils is, if Q is less than or equal to 1, those coils are called low Q coils. Next, medium Q coils, medium quality factor coils, medium Q coils. If 1 less than Q less than or equal to 10, those coils are called medium Q coils. The one more classification is high Q coils, high quality factor coils. If Q is greater than 10, those coils are called high Q coils. Okay, this is the classification of inductive coils based on the quality factor. Okay, this range is important in measurement point of view. You'll see which bridge is used for low Q coils, medium Q coils, high Q coils. Later on I will give. Which inductance bridge is used for low Q, which inductance bridge medium Q and high Q, it is preferable. Later on that I will discuss. But range also you concentrate. Clear? Okay, these points you remember with respect to the significance of quality factor means which measure the quality of a inductor. Given inductor is how much quality, that is measured by the quality factor. Understood? Okay, these points you concentrate. Clear? Quick note down. Yes, over. Now we'll see what is the significance of dissipation factor. Clear? Okay. Yes. Okay, dissipation factor. D. Okay, it indicates the quality of a capacitor, or it measures the quality of a capacitor. Quality of a capacitor. quality of a capacitor is measured by dissipation factor? Tell me. High dissipation factor indicates low quality of capacitor. That is important. Okay. High dissipation factor indicates low quality of capacitor. Low quality of capacitor. Next, dissipation factor is measured by capacitance bridges. Dissipation factor. Using some capacitance bridges, we can measure the dissipation factor. Dissipation factor is more accurately measured by measured by capacitance bridges. Capacitance bridges. Okay. Now, how we can define the dissipation factor? For example, let us assume that for a pure capacitor, let us consider a pure capacitor. For a pure capacitor, let us consider for a pure capacitor. If it is a pure capacitor, let this is C, then supply voltage is V. Okay, let the voltage across the capacitor is Vc, let this is I. For a pure capacitor, let this is V or this is current. The voltage across the capacitor leads the current leads the voltage. The current leads the voltage by angle of 90 degrees because it is a pure capacitor. Now this Vc equal to V. Vc equal to V. Both are same here. Voltage across the capacitor leads the current leads the voltage because it is a capacitor. No? That is, voltage across the capacitor lags the current by angle of 90 degrees. Okay, this is for pure capacitor. If you consider a practical capacitor, or this is perfect capacitor, pure capacitor or perfect capacitor, air capacitor, then the angle between voltage and current is 90 degrees. Clear? In practical capacitor, practically we can represent the capacitor having with some resistance also. Let this is the resistance of capacitor and this is capacitance. This is R, this is C. Now we are giving the supply voltage is V. Let the voltage across the resistor is VR, voltage across the capacitor is Vc, this is V. Okay. Now, can you tell me what the resultant V equal to? VR plus Vc. This is not a arithmetic sum, it is a vector sum. Now let the current through this RC is I. The current through the RC is I. Okay. Now if you draw the vector diagram in this case, okay, this is I, current lags the voltage, this is Vc. Always the angle between Vc and I is 90 degrees. But you know that resistive drop is in phase with current. Now resultant supply voltage is not Vc equal to V. Now the resultant supply voltage is, this one. Now this angle is 90 degrees. Now the resultant supply voltage is this one. Okay, the vector sum of VR and Vc, is the V. This is V equal to VR plus Vc. Okay, VR plus VC, and this is VC. Okay, this angle is 90 degrees. Now because of the angle between, I am talking about supply voltage without any resistance in an ideal capacitor. For pure capacitor, the angle between supply voltage and current is 90 degrees in a pure capacitor. Now the angle between supply voltage and current is not 90 degrees. Let it losses some angle, let it losses delta angle. Now the angle between supply voltage and current is 90 minus delta. Where that means due to resistance of capacitor, it losses some angle. That angle is called loss angle or dissipation angle. Therefore, where delta equal to loss angle or dissipation angle. Loss angle or dissipation angle. This angle we are getting because of the resistance of the capacitor. Due to resistance of capacitor, it losses some angle. That angle is called loss angle or dissipation angle. Okay. Now, I want to define what is the dissipation factor. The dissipation factor equal to D equal to tan of dissipation angle is called dissipation factor. Tan of dissipation angle is called dissipation factor. Now you define from this what is D equal to tan delta equal to D equal to tan delta equal to, it is a series RC circuit now. From this I want to write what is tan delta. This vector is VC. What about this vector VR? This and this is same now. Now I want to define tan delta. Tan delta equal to VR by VC. VR by VC. How to write VR? I into R. How to write VC? I into XC. Shall you write like this? Omega CR. Okay. Therefore, this is the dissipation factor for series RC circuit. Why you are getting dissipation angle? Yes, because of resistance of, in ideal capacitor, what is delta equal to 0? But in a practical capacitor, because of resistance of capacitor only we are getting some angle. That angle is called dissipation angle. Then that is T equal tan delta equal to omega CR. This is a dissipation factor. Shall you write like this? D equal to tan delta equal to omega CR. We know that in series combination quality factor equal to 1 by omega CR. That's why D equal to 1 by Q. In terms of quality factor, I am telling that. If the quality factor is increases, then if the dissipation factor is reduces, quality. That's why if the dissipation factor is less, the quality of capacitor is more. For series combination, what is the quality factor? Q equal to 1 by omega CR. But I am writing omega C equal to, you know this one. For series combination, Q equal to 1 by omega CR. From this omega CR equal to 1 by Q. Now I am telling that if the dissipation factor is less, quality factor is more. That is the meaning. Like that we can measure the quality of a capacitor. Okay. Now this is about the dissipation factor formula for series RC combination. One point to remember. Now here we can define the power factor also. What is the fundamental definition for power factor? Power factor equal to cos of angle between voltage and current. This is the fundamental definition for power factor. Therefore, power factor equal to what the cos of angle between voltage and current here. This is voltage, this is current. 90 minus delta. That you write cos of 90 minus delta. That equal to sin delta. Very important. If dissipation angle is given, power factor equal to sin delta. It is not cos delta. For example, in a series RC circuit, in series or in RC circuit, maybe series or parallel, this is applicable. In RC circuit, if dissipation angle is 30 degrees, the power factor of the circuit equal to dash. If the question asks like this, then power factor equal to, it's not cos, because given is the dissipation angle, then sin delta, sin 30. That is sin 30 equal to 0.5. 1 by 2, that is 0.5. Is it lagging or leading? Leading, because it's RC circuit now. Its RC combination means this is 0.5 leading. Like this you can answer. If the dissipation angle is given, power factor is not cos, you take the sine. Clear? Okay, this is what is the significance of the dissipation factor. I explained what is the significance of the quality factor, and this is the significance of the dissipation factor. Clear? But one more point to remember here. For a pure capacitor, what is the dissipation angle? For a pure capacitor, practically not possible. I am telling that for a pure capacitor, okay, what the dissipation angle? Delta equal to 0. What the dissipation factor? D equal to 0. What the active component equal to 0? Because active component is nothing but a VI cos of angle between V and I. What is the angle between V and I? 90 degrees. Cos 90 0 in a pure capacitor. Then what is the reactive component? It exists only reactive component is exist. VI. That is VI into sin 90. This is the reactive component. That means a pure capacitor does not consist of any active component. It consists only reactive component. That is important. One more point to remember. For a pure dielectric, pure capacitor, for a pure dielectric material, D equal to 0 and delta equal to 0 and D is also 0. Okay, these points you remember for a pure dielectric material. Okay, that's why one of the main application of this dissipation factor is a tan delta test is used. A tan delta test is used in transformer. Mainly a tan delta test is used to find the properties of insulating material. To find the quality of insulating material in a transformer, this important note you remember. In a transformer, a tan delta test is conducted. A tan delta test is conducted to find the quality of dielectric. To find the quality of dielectric. To find the strength of the dielectric. We know that in a transformer we are using a transformer oil as a dielectric material. Even some solid insulation is also used as a dielectric material. If you want to find what is the strength of the dielectric material, we can conduct tan delta test. If the tan delta is high, if D is high means tan delta is high, quality is less, quality of dielectric is less. Okay, if D is less, the quality of dielectric is more. Quality of dielectric is more. Like this, we can test the quality of a dielectric by conducting the tan delta test. By conducting tan delta test, we can test the quality of dielectric. Okay, this is about what exactly the significance of which one? Dissipation factor. The dissipation factor is more accurately measured by which one? Capacitance bridges. That point you remember. Here I given for pure RC circuit. Then for parallel RC, this is a series RC circuit. I given the formula. But for parallel RC circuit, directly I am giving the formula that you concentrate. Now see, for parallel RC circuit. For parallel RC. Yes, this is for parallel RC circuit. This is R and this is C. Then if it is a parallel RC circuit, the dissipation factor D equal to tan delta equal to 1 by omega CR. The dissipation factor equal to tan delta equal to 1 by omega CR. Okay, that it is also derived based by drawing the vector diagram for parallel RC. How to draw for series RC combination, that I explained. You know, even in the AC analysis that you studied how to draw the vector diagram for a parallel RC circuit, that you try. Then you prove that D equal tan delta equal to 1 by omega. We know that in a parallel combination, what is Q equal to? for parallel circuit, Q equal to omega CR. Q equal to omega CR. Now you substitute here D equal to tan delta equal to, this is the relation between quality factor and this. Always quality factor and dissipation factor is inversely proportional. That means high quality indicates low dissipation factor. If the capacitor is having the low dissipation factor, then we can say that capacitor is having the high quality. Okay, this about in detail what exactly the significance of dissipation factor and quality factor, and what is the different types of AC bridges we are using. This is one concept important for theory questions that you ready to answer. Clear? Understand? Quality factor does not have any units. It is a constant value. I am telling that now. XL by R. What are the units of XL? Ohms. What are the units of resistance? Ohms. It's a constant value only. You don't have any units for quality factor. Okay. Even dissipation factor is also constant value. It does not have any units. Clear? In the next session, we'll start with in detail about each bridge. First, I will start with inductance bridges. First, I want to discuss inductance bridges. Okay. Later on, I will discuss the capacitance, frequency. Then finally, I will give some important points with respect to mutual inductance bridge. In detail discussion of mutual inductance bridges not required. Clear? That you concentrate.